Welcome. This video is going to be about our homework for week 2, and I'll be discussing specifically the use of free body diagrams to find net force and also to make calculations about acceleration or mass using Newton's second law of motion. So when we look at the homework, one of the first things it asks you to do is go through and to actually make some free body diagrams for objects that are either at equilibrium, constant speed, or coming to a stop. And so these terms, equilibrium, we discussed last week about how that means that all your net forces must equal 0. That tells us a lot about the amount of force you have and then in what direction it is. And we're going to be using these forces specifically for these examples that follow. And those forces are going to be force of gravity, which is F sub g, tension force, which is F sub t, normal force, F sub n, and then friction force. The normal force we talked about in class. Remember that force is going to be the force that opposes gravity for situations where objects are sitting on top of something like a table. We discussed as the example in class, we talked about as you guys were all sitting in your seat, the force of gravity was pushing you down into your seat, but then the normal force was a force that went against gravity in an equal amount to put you at equilibrium. And that normal force is what opposes gravity to keep you in that seat, not moving. So let's go ahead and take a look at this first example to talk about how you need to do these free body diagrams and how they need to be labeled. So when we look at this first example, you see that this rock is being suspended by a string to a ceiling. And when we're trying to identify forces, remember free body diagrams are going to be starting with the object itself, and then we'll draw the forces qualitatively, which means that we're going to pay attention to the size. And if the object is in equilibrium, we know that the force of gravity that's pulling down on this rock, so the force of gravity here, is going to be equal in size to the tension force in the string. Try to draw those as equal as I could. So this is the force of tension in the string. And again, I've made them equal because of the fact that it says it's in equilibrium. We know that the tension force must equal the force of gravity, so that when we find the net force on this object, it comes out to be 0 newtons. We know that it's 0 newtons again because of the fact that it says equilibrium. So as you work on these problems, make sure you pay attention to that. If it's talking about an object that's in equilibrium, that means that the forces going in opposing directions must cancel each other out or be the same size. So make sure you make the arrows the same size when you draw them for these vectors of force so that the net force equals 0. Another key word that you can pay attention to that goes hand in hand with equilibrium would be something like constant velocity. And the reason I bring up constant velocity is because if you have constant velocity, that means your acceleration equals 0. And if your acceleration equals 0, you guys know the equation for second law is force equals ma. So mass times 0 will give you a force of 0. And so again, it basically leads to the same conclusion that if you have a constant velocity here, that we're going to have all of our forces balancing out in that direction. Because if they were unbalanced, then we wouldn't have a constant velocity. You'd have an acceleration. Okay. So the other example I wanted to go over for the homework, and you can see here that 1 through 8 are all very similar. You're just doing a free body diagram, and you're paying attention to the wording of the object's description for what it's doing. And again, here's an example right here, constant velocity. That means that whatever forces are acting on this object are going to end up being equal in opposite directions, so they cancel each other out. But this is the second problem I wanted to go over, the rock hanging at equilibrium. And I wanted to go over it in terms of how you could use the things we just talked about to solve for something. So if we look at that example, it says that the rock is hanging at equilibrium, and they actually give you the force of gravity here. They say the force of gravity is 50 newtons. So if we're doing a free body diagram for this rock, you'd have a force of gravity going down of 50 newtons. And we know force of tension, because it's at equilibrium, We know that the force of tension here is what we're looking for. If we had to have an equation for this, it would be that the net force is equal to the force of tension when we're doing top minus bottom, force of tension minus the force of gravity. And one thing that I didn't put on here, but that I should have at the very beginning, because it's an equilibrium, we know that the net force is equal to 0 newtons. So now that we have our equation, we know that we're taking top minus bottom because these forces are going opposite directions. We just fill in our values and we would end up with a substitution step where we had 0 newtons equals the tension force, which is what we're looking for, minus the 50 newtons, the force of gravity. So to solve for tension force, we just add 50 newtons to both sides. Cancels here. And you end up with tension force is equal to 50 newtons. So to review the steps, again, at the very beginning, they gave us the force of gravity. We went ahead and assumed that the net force was equal to 0 because of the fact that the rock is in equilibrium. We knew the thing we're looking for was the force of tension in this string. The equation for net force would just be the top force minus the bottom one, force of tension minus force of gravity, because they're going in opposite directions. When you plug in the values, you put 0 newtons for the net force, you put 50 newtons for the force of gravity, and then you just simplify this expression to solve for the force of tension in the string. Okay, so you're going to follow that kind of thinking to finish the rest of the problems here. And they've given you some given information, and then you just go about solving it using Newton's second law of motion. And again, just to reiterate this, just make sure that this last part you're teaching somebody and that they're going ahead and filling in the rest of it for you based on the conversation that they have with you about the homework and whether you understood it or not. The other thing I want to point out is that I do have tutoring on Wednesday, Thursday, Friday mornings, and then also during the week in the afternoon on Monday, Tuesday, Thursday, and Friday until about 4:50. So if you have any questions about the homework, you can come during that time and I can help you get caught up on anything you need help with.